All right, so what week is this? Week 6 right now?
Yes.
All right, so let me look at this. 5.4 we're coming back to. Okay, so you just read 5 this. So now we're reading, so for next week we're going to do memory. Then we're do input, output. Okay, and this is just our simulator. Okay. So you read this for that week. So next week's week 7. The week after, then for the next week you'll read this one, and that's week 8.
And that's the week of fall break.
That's the week of who?
That's the week of fall break.
Are you lying? But the fall break's at the end, right? Oh, we are on a Thursday. When does fall break start?
The 24th.
But is that Thursday?
Yeah.
It is.
Oh, okay. Well, so then I'll probably give you this as a reading assignment.
Well, that would, I guess, yeah. That would be,
We would have it read by the.
yeah, we would have it already read by then. Hypothetically.
Yeah, because you're reading this for next week, and then you'll read this for the week after that, but we wouldn't have class on the 24th, right?
Well,
Wait, that would be
technically-
done by before break. That's the
Yeah,
fall break.
presumably you would read this as for to be due on the day we would have class on the 24th. Yeah, right? So you'll read this for next week.
Read chapter 6 for the 10th, read chapter 7
7
for the 17th.
Yeah.
Oh, okay.
And then fall break is the next week.
Gotcha.
Technically, graduate classes don't fall.
Yeah,
Fall
we'll
break is
yeah.
something we don't like saying.
Yeah. So what I'll do then is after we do, we'll talk about chapter 7, and then what I'll do is for, we'll just say homework for the fall break class, I'll put up a an exam on Blackboard. So what date is this class? You said this?
October 24th.
No, that's the break. What date is
The
The-
week before that? 17th?
yeah?
The 17th.
So you've read this for the 17th, right?
Uh-huh.
We've had our class, we've talked about it, done our stuff, whatever. So then for the, I won't give you a homework assignment on the 17th because we won't have class on the 24th. But what I'll do is I'll put up an exam that just needs to be completed before our next actual meeting, which will be the 31st. So you have 2 weeks to, once you start the exam, you got to finish it, and I'll give you whatever, plenty of time for the exam, but so you can just finish it sometime in that 2 weeks, because then the second 8 weeks we'll have a fresh start to like a new subject, because we're going.
I haven't really looked at that next subject yet, have you?
I haven't looked at this tab yet.
No, the next subject to like the next half, have you?
Correct, no.
Okay. I'm just like curious how to, like,
I thought we were gonna do data.
Data science, yeah, it's right here.
That's what I'm saying.
She asked me if I looked at it yet.
Oh, I thought you thought about it yet, like as far as like what we're planning on doing.
Well, I'll figure it out. It's gonna be awesome.
Oh, so that's a no.
Yeah, no, I mean, like I said, I've
I'm
now
an optimist here.
I've now looked at this tab that says 7 because I clicked it to see what was in there, but I haven't clicked the memory tab yet. So we're gonna leave that as a surprise.
Yes, you clicked the memory tab. I watched it.
No, I clicked this one, this tab.
Go back, stop the recording and look. I
Ooh.
remember seeing
Did I really?
Evidence.
Yeah.
I definitely did not click that one. Now I
You
did.
did.
No way.
No, you did.
We're gonna look it up.
Well, look it up. I'm gonna be right. But now I've looked at it. You can't count
I don't
this.
remember, so I have no opinion.
All right. So, where was I? 5.4? All right. So, so now they're talking about the how registers are actually built. So these guys are built in terms of a sequential circuit. So sequential circuits have state, which means that. So remember a little bit ago I was talking about how like for like a MIPS processor, for example, might be on like a 2 megahertz clock or something like that, where it pumps, it pumps, it pumps. So the previous state might have an impact on the next state type thing. So these guys maintain a state. So they're talking about the clock and this thing called the rising edge, which you're leading up to the next state. Remember, so this is an instant. 0 changes to a 1. Remember when we were looking at the timing things, I said we weren't able to play when it goes from here to there. You don't get any say in that transition. So they're calling that the rising edge. Let me just click back. It'll take 2 seconds under timing diagrams. This is a rising edge right here. This is a falling edge in that one. But whenever you're transitioning from a 0 to a 1 or from a 1 to a 0, that is an instantaneous thing in digital logic. We don't get to play. So that's your transition, call it transition no time. It's the speed of light. Speed of light minus resistance, because technically we do have copper wires and stuff involved here, so it will be slightly slower than the speed of light just because copper has a level of resistance, but it's going to be fast. Anyway you cut it, it's going to be fast. So you don't have a whole lot of time to interject anything in there. All right, so we have this clock, how often something pumps. All right, and then what's happening on the next move, typically from an input or something like that, and that might dictate what the next output is going to be. So for instance, with a, this is going to be a reset. This is a load. What's this guy in there? Oh, that's the reset. That's the load. So what's this weird dude? And bit values, loading bit values. The register should be loaded. Okay, resets it to a bunch of zeros. And reset has priority over load. That makes sense. Oh, this must be the clock. So this is the pulse that moves to the next thing, is what I'm guessing. I haven't done. Yeah, I don't see it mentioned up here, but that has to be. Where? I see this.
Quick play.
And I see this. Oh, the start?
Yeah. You have to scroll down because that's where it tells you words, yeah.
All right, what do I do? Okay, I click the play button. Clock rises. That has to be the clock. Yeah, it's the clock. LD, reset, and the clock. See, okay. All right, so this is the guy that tells the circuit to pulse, the sequential circuit. So this is going to happen however often it's going to happen, depending on the sequential circuit that's being built there. You know, there's going to be some sort of timer. Usually the clock on a CPU is measured in, well, way back was measured in hertz. Today's it's in gigahertz, right? You know, 2.4 gigahertz, something like that. That would be the timing, the clock on it. And typically that's the number of cycles per second. So 2.4 gigahertz would be 2.4 times 1024 megahertz times 1024 kilohertz times 1024 hertz. So hertz would be cycles per second. So that means that the clock fires 2.5 billion times a second. I want to see our modern day CPU. something like that. That still doesn't necessarily tell us a huge story about the architecture and what the architecture can accomplish, but it tells us how often the architecture can try to accomplish something. All right. Okay. Okay, so just explaining how this works. I'll just do it on this one here. So we have, this is the inputs feeding into this register. All right, so this is those 3 electrical signals coming in, zeros or ones, feeding into it. We have the current state of the register. Okay, and the current state of the register becomes the output of the register on the next pulse. Make sense? So from this guy right here, when it pulses, 110 will come out of here. The assuming these are the inputs, if these are the inputs 0, 0, 0, when a pulse hits the load, that will say take from inputs into this guy. A reset would not take anything from inputs. Instead, it would just set this all to 0. Set the current state of the register to 0. All right, so whenever a signal comes into RST, reset, these become all zeros. Whenever a load hits, whatever's poised out here, trying to set its value, gets loaded into the register, and that becomes the new value here. I wonder, does it push out the existing value or only, actually it would, because it would be on the next clock. So the important thing to look at this is if you do a load, then this value comes in, this value goes out. If you do a pulse on the clock, I don't think anything will actually come out of that register. All right, so there's our original thing. So we pulsed on the clock.
What does that mean? Like,
What, the pulse on the clock?
yeah.
So it's how often, so you were in the game programming class and we did stuff in update. So once every frame, something happened. So this is kind of like that. So once every some fixed amount of time, which is the clock speed of our CPU or the clock speed of the whatever's pulsing, whatever's giving this guy electricity. So he's telling the sequential circuit to advance. So let's just say it's once a second. And a little example. So the initial state of this guy, am I at the initial state? Okay, so the initial state of this guy right here is we have a empty register. So he's already in his reset state. This is a register that has 3 bits in it. It's a 3-bit register, all zeros right now. So let's just say our clock is 1 second for simplicity's sake. So after 1 second, notice we have some dudes here at the door. So after 1 second, something happens. So the clock hits, now the circuit is prepared to do something else. Now this guy knows how to do 2 somethings. He knows how to either load something or he knows how to reset himself. All right, so on stop 2, does it tell us what is happening on stop 2? Okay, on stop 2, we still have 0 on the load. Notice on the first stop we reset, so we had it at a, still have all the zeros there. So we confirm the register was reset by actually feeding a 1 to reset. So on our first clock cycle, we reset the register to make sure we had a 0. That's why the current state of the register is a bunch of zeros. They're showing us what the inputs are coming in, but we're not using these inputs yet. These don't do anything until we load. Remember, this goes back to our MIPS assembly. We load from memory into a register. We store from a register into memory. Make sense? All right, so we're waiting for a load to fire, for there to be an electrical signal that comes to this, for a 1 to be delivered to the load, for these guys to make their way into the register. Okay, so we'll hit 3. What happens on 3? 3, we have a load. All right, oh look, he's been animated. See that? That was awesome. Do they always do that? Watch them slide in there.
Where my mind's going from.
All right, so, and the reason those inputs were allowed to settle into the register is because on that clock cycle, here's our timing diagram, a load was a 1. All right?
And we're the ones setting the load or the reset? That's not automatic, like the pulse thing?
The clock happens on its own. Yeah, we're not doing that.
But the other two?
Yeah, those would be like somebody's input. Yeah, somebody's saying reset the register, somebody's saying load the register. That would come from some assembly instruction. Okay, so we have now loaded that register. So now it's holding its value. So now we have, new input 0, 0, 0 waiting at the door, but not until we hit another load do those come in. So on that last cycle here, we had no load. Okay, here's our D0, D1, D2. So we have all our zeros right now on that clock cycle. So that's what's sitting here right here. Our register still holds the value it previously held from our previous load. So on this clock cycle, we delivered zeros to our input bits, but they aren't taken yet. We just delivered them at this point. So zeros came to zero electricity, off energy came to the input bits. But we are not doing a load and we're not doing a reset. So neither of these guys fired there, but we did just do a clock cycle. So now we're going to say 1 second later. That's what we're pretending like our clock cycles are on. Oh, we're on a different thing now?
I was lost the whole time.
You were what?
I was lost the whole time.
Okay, hold on. Let me just see what he's doing.
Maybe it's just parsing it out into different things.
Well, this might be like the black box. So this is your inputs on D. So this is showing you what's underneath the hood. Well, and then this is kind of the top level register. Like, we know registers store values. So this current guy here stores a value. What value does he hold? 0, 1, 1. This is the D register, I guess, whatever they're calling it. So 0, 1, 1, that's the value he holds. And then, or 1, 1, 0, however you want to read this. This is in reverse endian.
Okay, that would make no sense.
Remember the reverse endian thing we talked about? Was it 2 times ago, 1 time ago, 5 times ago? All right. And you thought I was making up the word? Was it you? You thought I was making up the word? Ha. All right. So, actually, it's not reverse. It's little endian. So this is instead of big endian. All right, so that's what this is showing. This is showing us if you were to pop the hood on the register. So over here on the right is the register. So maybe this register is called D and the output is Q, let's say. But we know there's stuff happening under the hood there where it's actually stored, but we don't care about that right now. We kind of saw under the hood over here. Now they're showing us a little bit different view of the register. These guys are all the same. It's the same timing chart here. Okay. Our last timing, we had no load, we had our clock, and we have no reset. So this dude is still holding his value of 0, 1, 1 or 1, 1, 0. Click on 6. Now we're going to do a load. We are. So we do a load. So there's our clock. So the clock hits there. We get a 1 on our load. And then what ended up happening? We had, well, let's see. Hold on, I want to back up there. That guy was doing a whole lot of dancing. That's our 1, 1, 0. Then we hit the load. Okay. So this is showing 2 separate registers. That's what's happening here. So this guy is this register right here. So we did a load on that register, and what did it do? It brought in the inputs, which were 101, pushing out an output, which was the thing that used to be in there was the 110. And then that was fed in as input to another register over here, which also had a load go to it. So that load allowed that register to have the value 110. So this is like we loaded this this register and stored the value of this register. We temporarily stored the old value of this register to make room for the next value of this register. Does that make sense? We don't know why they wanted to do that. That's just what they did. So this is the register. This is open heart surgery on the register. So we got the top off. This is a high level view of one register. This is two registers working in sequence.
Okay, but what's the heart reference?
Open heart surgery. This is a register that has the top open, so you see the value that's sitting in there, and you see the internal guys coming in, where with the top on, you only see one input, one output. You don't see the value in there. Right? It's heart surgery.
You just didn't continue with the analogy, so I'm so
Really? I thought it was obvious. All right, so does that make sense how a register works? A register has state, and things can get loaded onto the register, which makes the register change its state. The register can also reset, which resets the state of the register to a bunch of zeros. Doesn't matter what was knocking on the door. A reset will, I think they said reset always takes precedence over a load. Right? So if we had a 1 hit load and reset at the same time, the end result of this register would be a 0, a bunch of zeros, because reset is more powerful than a load. I think they set that up here, didn't they? Yeah, reset having priority over load. Okay, so if your sequential circuit, for whatever reason, delivered a 1 to an to a load and a 1 to a reset on the same clock pulse, the final state of that register will be 3 zeros in this case, regardless of what was standing at the door to load. All right? Keep in mind that registers are still built in terms of those OR gates, AND gates, the same things we talked about earlier. Those are the primitive types for building our circuits. All right, but what they're showing us here is effectively a sequential circuit. What they're showing us here is memory. So remember, what is a register? When I say hardware registers, what am I talking about?
that's the stuff close to the CPU, right?
Yep, so it's like a variable made out of hardware. And variables are how computers, programming languages, whatever, mimic our memory, right? So a register is a little tiny spot of memory. You just store a little tiny bit of memory. Now, in order for memory, this kind of memory, so this would be, I guess, static memory. In order for this guy to hold its value, it needs electricity. Electricity is kind of the thing that keeps the value there. Is if you yank the power cord on your computer, the computer shuts off. Whatever was in your system RAM is gone. Whatever was on your CPU's registers, an L2 cache, L1 cache, gone. Hard drive's still there. That's a different kind of memory. Okay, it's that is called non-volatile memory. This is volatile memory. Volatile memory requires electricity to keep it going. Okay, so that's where we have electricity constantly playing a role on this guy and then pulsing to advance the next instruction. Or if we think about this from the CPU's perspective, the CPU kind of eats instructions as they're coming in. So each pulse, the next instruction does something. And depending on what that instruction is, something happens, because registers are part of many of the instructions, right? Something is going to happen with this register. So registers can load things, or registers can reset themselves. How do you get a value out of a register? By calling load on that register. It pushes the existing value out. That make sense? So we can put zeros in there. So when you do a 0 at the door, that push it, and then you do a load, that will give you an ultimate reset on it with values firing out. Whereas if you just do a reset, these just become zeros. You never fire the value. So if I want to get this 110 out of here, I would load 000. That would leave my register in a reset state. But I accomplished that by loading zeros, and then that would cause Q0, 1, and 2 to fire 110, which in this example over here got provided to this other register, whoever that is. And these registers are all hooked up to the same clock. CPU is saying this is our cadence, 1 every 1 second, let's say. Every 1 second, something happens. All right, that makes sense how that guy works? All right, so that's an example of how memory at its smallest little thing functions.
Yeah, so could you just do one of these exercises on
With
5.4?
this one?
Yeah, if you can do like the third one.
Do I have to hit start or I just answer?
Yeah, you have
Well, I don't think you can choose which
You
one
have to
does.
do 1 and 2
Yeah.
if you want.
So I hit start here?
Yeah.
All right.
Oh, I think I know what the third one was.
All right, so
One and 2
all right,
would
so
offset by 2, right?
so
Yeah.
A is a 4.
I don't know why it grabs like 3 zeros.
How do you know that's a 4?
It's right here,
Oh, okay,
right? So A is a 4. So we're on our timing. So this is our various times. So we are doing a load initially. So a 4 would come into here on that initial load. So this is our rising edge here. So on the rising edge, we do a load. So we got a 4. Well, this is actually showing us the state of A. All right, so we have a 4. And then they want to know what the value of Z is. Is this what I'm supposed to fill in?
Yes.
That's where my answers go. Okay. So right now, Z is a 0. At this point, I've loaded a 4. Z is still a 0. Okay. Now load is off. And we're not resetting or anything. So load is still off. So now we hit this rising edge here. So we're loading something else where A is a 2. So a 2 is going to get pushed into here, and a 4 is going to get pushed out. So at this point, when a 2 goes in there, a 4 should come out there. Do I have to check now?
No, you
You
have
have
to
to finish
feel.
it.
Oh, I have to keep. Oh, okay. Yeah, I'm not checking each. So this is one puzzle, and then 2 will reset this into a new puzzle. Okay, got it. So a 4 will come out. Then we are on still a load with a. Actually, my rising edge was here on that guy. So now we fall, and we're on. Yeah, that should be it.
So should that 4 be in the spot over?
4 it should be in all of these because Z should have
Oh.
fired a 4. What didn't it like about my?
So I think.
Oh, load's on here.
Yeah, because it's clocking, right?
Yeah, but hold on. How's this? So this guy, are we supposed to?
Clock rise, so in the next one, the second one should load for.
Well, yeah, but it doesn't. This is the what do they talk when they say expected Z? What do they mean? Do they mean what Z will be?
I don't think input and output is different.
Well, right. So the thing is when they say what does that mean?
Oh, because you clicked next.
It resets.
My
So it's a new puzzle.
so this but it's still level 1. We're still in the okay.
Yeah.
So that's
Still
fine.
the same idea.
That's fine. So I'm thinking down here, this Z, they're asking what will the expected Z be? Because that at some point it's going to be that. So here's our first rise, and we've loaded a 2. So at this point in time, our expected Z would be a 2, based on that.
Yes.
Here's our next rise. Now we've loaded a 2. We are not. The 6 is waiting at the door here. So the 2 is actually still stuck in here.
Yeah.
So this is still 2. This is still 2. Then we have, this is still,
No.
where's my next rise? My rise is here. So this one is still 2, and then we hit our rise with a load, so that will actually push the 2 out. So now our expected Z became the actual Z. And now we have a 7 in there as our expected Z because that's the new value of our register. And we don't have another thing, so we just leave it as a 7 there. So that's really weird that they would talk about what's the expected Z. Because it doesn't become Z. That's the value of the register, but this register doesn't have an output until something is requested from it. But I guess the value of this register is it's a static value as long as there's electricity coming to it. So we could say it's fair to say that Z will be that value, but Z doesn't become that value until it actually fires out of this register. If we view this as an output.
Until it loads, it doesn't really.
All right, so then we do the next one. So the next one we have the first clock cycle is here where we have a load, so we have a 4 here. Then we have still a 4 here. Then we have a rise, but still a 4 here. Still a 4 here. Then we have a rise, and that becomes a 2. Then we have a fall, so this is still a 2. All right. I click next.
Yeah.
All right, so we have
Yeah, I got 2 different
I got-
registers at 3. So that's interesting that you only have still 1.
Why is yours easy?
All right, well, we'll see. Maybe 4 will be
Right.
different. All right, so this is a 1.
Just click submit.
Oh, so I do check? Okay, so now I can say next?
Yeah. There you go.
Yes.
Okay. What do you mean I have 2 different registers? Oh, over here. Got it. But we're still only talking about an input of A and an output of Z.
So it doesn't change anything?
Well, it would, because Z, your expected Z is actually over here. So Z doesn't have an expected value until this guy has a value, this right register. And this right register doesn't have a value until you've loaded, done a load overwriting the first one, which pushes it into the second one. So we have our load bits on both of these. Are we supposed to assume these guys are connected? Let's just assume they're connected. That this load controls both of these registers.
The same clock. That's all.
All right, so we have, well, yeah, and that way that makes sense. It's the whole CPU is pulsing. So on this first rising edge, something happens. What's happening? Our load is happening. But what's actually being loaded? This register right here has a 3 coming into it. Okay, but Z does not have an expected value yet. So Z is still a 0. Z only is going to get an expected value when we have something that comes out of here. All right, so for right now, I don't have a way of keeping track of it, but there is a 3 sitting in here. All right, next rising edge, a 1 comes into here, and a 3 would show up there. So when that 1 gets pushed into here, it pushes the 3 into here, which now gives us an expected value for the Z. First rising edge, we have a 3 here. We have a nothing here. So there's nothing for Z. That's the first rising edge here. Next rising edge, a 1 pushes the 3 out of the way. The 3 moves into here, which now has an expected value for Z of 3. Still a 3 here. Next rising edge, we load a 0 into here, which pushes the 1 into here. So we have a 1 and then a 1. Does that make sense how that's working?
So I tried to do the Q first, then press the
the value of the Q set at A, but I try to plug everything back again, but I keep getting 1, 0 less in the beginning.
All right, let's do another one.
Okay.
Okay, let's do another one. What's unfortunate is they're not giving us a little bucket here to like kind of remember what the current state is. So the important primitive thing to think about here is that remember that the value that's stored in this register does not get into this register until we've loaded this register the second time. The first time we load our register from A, so A is a 3 here, right? So we have this whole thing's loads forever, right? So on our clock up, or what do they call it? Rise, clock rise or whatever. So this is when something's happening. What's happening? A load is happening. What was my input? It's a 3. So at that point in time, a 3 comes into here. So I want to draw a 3 on the screen right here. But nothing has happened to this register, because this register did not have a value yet. So this register is still dormant, let's say, which means that Z has no expected value yet. But I do have a 3 sitting in here. All right, so that's on the first rise. Next rise, we're loading a 1. So a 1 pushes into this one, which shoves the 3 out. So now the 3 is sitting over here. A 1 is sitting here, but now Z has an expected value. The expected value is the 3 that just made its way over to the second register here, because the 1 took its place in this first register. So my current state of my registers here is a 1 is sitting in here. That will be the next output for Q, or next input for D, we can say. But Z will have an expected output of whatever's currently in that other register, which is a 3. Still a 3 on the cycle down. State didn't change. On the cycle back up, we have a load. What does load say? We're going to load a 0 in here, which pushes that 1 out. And when we push the 1 out, it pushes in here, which pushes the 3 out. So now our new expected value for Z will be the 1 that's in here. Okay, because the 1 was here and the 3 was here. Then when I loaded the 0, the 1 got pushed out of here into here, which then pushed the 3 out of here into here. So 3 is now gone. We've lost its value. It fired out as Z. That was the old expected value of Z. My new expected value of Z is a 1. This last downstroke here, let's say, we didn't have a load, so the state of our registers didn't change, so it's still a 1. That makes sense how that's working? All right, so this is showing you the example of how 2 registers work together. But the important thing for us is know that a register's state does not, well, a register's output will not happen unless a load occurs. A register's state changes whenever a load or a reset occurs. Because a reset would change its internal state to a 0, but it wouldn't push anything out. So if I had a 3 in here and I did a reset, that 3 would not get pushed over here on a reset. But if I wanted the 3 to get pushed over there, I could load a 0, which would effectively reset this register, but push the 3 over to this other register, or push it out here and go into wherever it's going to go. Make sense? And keep in mind here, this does make the assumption that I don't know that they really drew it that well, that all of the loads and resets here are all in the same signal. Whenever this guy loads, this guy loads. Because otherwise, if I had a 3 in here and I loaded a 1, let's say, that 3 would push out here, but if this guy wasn't also loading, the 3 would never make its way in here. So they both had to be prepared to load in order for this door to open for the 3 to flow in. All right, so does that make sense how that guy works? All right, register files. All right, three-state buffer. So this guy is saying, what does if we look at this as a function, okay, and we get a output of y. So b is our input, y is our output. This fires a 0 or high impedance. So that's our whole resistance thing. So we get the value of b whenever a is a 1. That's what this guy does. So if I put electricity into the top of this three-state buffer, whatever value b is will be delivered as the output of this buffer. But as long as I have this turned off, because think of when you see buffer, what does buffer mean to you? Where have you seen that before?
Buffer something that it's keeping some information until that's there.
Let's keep it less. We'll keep it in this technical world still. If you put on Netflix and it says buffering, what's happening? Huh? So what's loading?
The video.
So why do you have to buffer it? Is your internet not fast enough to deal with it in real time? So based on the speed of your internet, you have to start, if you think of your movie as being like a jug of lemonade, okay, and you're pouring it out, you need to make sure that for an hour and a half, you have lemonade to pour.
Is it not always buffering? Like even if it's running?
Well, it is always buffering, but it has to buffer enough to start playing,
Right.
right? So based on the current speed of your internet, you're starting to fill up this jug of lemonade, let's say, and your movie can start playing as soon as you can turn the lemonade over and have it spill out at 30 frames a second. And your lemonade is constantly getting filled back up at the point where as long as you're delivering at 30 frames a second, you can make it all the way to the end of the movie without your jug of lemonade running out. So buffering is collecting data to be used later. Okay, that's what we're doing. So if you start a Netflix show and immediately hit pause, you might see that your buffer fills up, right? Up to a point. I don't think it'll just download the whole movie, but it gets a pretty good lead on you. So things would have to go substantially poorly. Because sometimes you'll have like a hiccup in Netflix where your internet connection speed drastically changes somewhere in the while you're watching your show or whatever, and it didn't plan for that. It started playing your movie based on your original buffer speed, and then all of a sudden things weren't working out so well. But idea is that if you pause it right away, it'll buffer for a while until it says, okay, we got enough of this movie, we're good. Well, because it is kind of a wasted bandwidth. Because if you started a movie and hit pause and then just walked away, it might download your 3 gig movie and you may never hit play. Something like that. I'm sure they did some sort of market research on what's the average, something or other. But, the idea is that what is buffering? Buffering is storing a value for later use. Make sense? So that's worth putting in the notes, isn't it?
But I think for networking, or more or less, the more common thing is saying your computer saying like your computer needs the data, but data sent too quick. Your computer cannot really processing it out. So those data are being saved in buffer for.
Yeah, but it's still the same definition. We're changing the way we might be using that buffer, but a buffer is still to store a value so that we can use it later.
What I mean is
the size of the buffer changes in what you're talking about. In this case, if I only have a 1-bit buffer, for example, which is the example they have here, this would be a 1-bit buffer, where if we're watching Netflix, it probably isn't going to cut your 4K movie if you can only buffer 1 bit of it, right? You want to probably be able to buffer 400, 500, 600 megabytes of it to kind of get a nice lead on there, right? Whatever it is. So, this is a super, super, super simple buffer that says, I am storing a single 0 or 1 for you whenever you need it later. You just let me know when you need it. And how do you let it know? By giving an electrical current a 1 here. Give me the value. So this 3-state buffer boils down to the value of B whenever A is a 1. Otherwise, this guy is in a high impedance state, which says, I'm not giving you my value. There's no output from this guy, no electricity. Highly, highly resistant. Make sense?
Is that equals to infinity?
It's equal to 0. If you're doing our logic on this, Z effectively will be no input to the next guy. All right? But the reason they're specifying it as high impedance is it's not an input of 0. It is no input. Okay, so if this guy was feeding into the A for another 3-state buffer, he's not delivering any electricity. We don't want to waste electricity. Make sense? So this is Netflix at the 1-bit level. Huh? Netflix. What did I say? Netflix? That's what Mr. Gonzalez is. He's inventing that for people who knit.
Like a Netflix.
Whatever. It's Netflix at the 1-bit level. So if you ever need a bit later, 1 bit later, you use the 3-state buffer. All right. That makes sense? Okie dokie. Oh man, this guy looks terrifying.
Exactly.
All right, so
It just makes you want to cry.
but hold on. This should be way more comfortable now based on what we've talked about today.
We have to talk about all the
Yeah.
basic things.
Because we've talked about a whole bunch of primitives today, right? We've talked about registers. So this guy looks like our register, right? We got the little load there. We got the clock thing here. So that's a register. That's a register. I even put reg on it. Reg 0, reg 1, reg 2, reg 3. Okay, what are these guys over here? 1 input, multiple outputs. Decoder. Yeah, that's our decoder. All right, so we're starting to recognize these guys in the wild now, right? Okay, so we see a decoder here. We don't know what he does, but he's a 2x4 decoder. And look, it even labels it. Decoder, 2x4 decoder, 2x4 decoder. All right, so this is a 4x8 register file. So we have 4 registers, and this guy gives 8 outputs for 8 bits. So this is an implementation of a 8-bit register. And let's see, this guy is the input from here. This guy is our switch.
Right.
Because the decoder took an, we just have, no. So yeah, this is our switch down here. This is our inputs into the decoder. So depending on what this input is, it's going to fire one of these guys. Yeah. 0, 0, 0, 1, 1, 0, 1, 1. 4 states. So we have 4 unique representations for this I0, I1, which translates into 4 unique outputs here, depending on what our switch said here. All right. And these guys, so if we just look at this top one, and do they tell us what D0, D1, D2 is? So this is RB, D0. Here's our clock on this register file. Does it tell us what RA is? All right, so this is showing you our, this is the open heart surgery version of it. So we're seeing everything under the hood. This is it all closed up. So all closed up, we have, so is this 8 bits, 8 bits? So this is read data, and this is write data. So we have one write, one way to write to a register, and we have 2 read ports on this, each serving 8 bits. So this guy stores 8 total bits. We can write 8 bits, but we can read from it from 2 different outputs, in case that is beneficial for performance, because you might have 2 things at once that want the value from a register file, something like that. So this is what this guy looks like, all closed up. So we have 8 bits that come in for writing. These guys up here, this is the write address. Is that going to be an offset? So it tells what the EN is.
It allows or not allowed. I just know that. If it's gonna be 1 or 0 there.
Is picking which register?
Oh, no, is it picking which register or which decoder?
The decoder picking which register to.
Oh, this is the EN. Yeah, so the EN here is our switch on our decoder to determine which of our 4 registers it feeds into. So just to quickly go back, I'm going to show you. What was it? The second thing for decoders. Here's our decoders.
I also forgot what the EN do.
That's our adder. So this decoder has 2 inputs. So the decoders they showed us here. So the EN thing would have been down here, which I'm thinking this decoder must be as a sequential circuit. So it doesn't allow this to fire until electricity is delivered here. So this isn't a which switch. This is we have inputs waiting at the door. When you have something fire here on that EN, it says that this decoder should decode its input and do what it's going to do. And I'll.
You said a write enable control signal.
Yeah, so if it's 1, you can do whatever is.
Otherwise, it does nothing.
Yeah.
Let's see where we at here. This was register files. This guy here. All right, so this, in their model here, they're actually not showing you these 2 decoders here. So they're pretending like there isn't input coming into these, but they're showing you how they would work based on this guy up here. So this guy has the address that we are going to. So we have 1 of 4 addresses, because this is a 2-bit input. 2 bits can be written in 4 unique ways, right? 2 to the 2 power 4. All right, so that's going to be the address where we're going. And whether we let this guy fire. So this is 2 bits input coming in here. As soon as this is a 1, the one of these 4 things fires. And these 4 things, so the D0, D1, D2, D3, whichever one fires, what that does is it hits the load on one of our 4 registers. That makes sense? So it's triggering the load in one of our 4 registers. Now, when a register says load, what happens? We just did all those puzzles in the previous thing. A load means whatever the input coming in takes over the value of the internals of that register and pushes whatever was in there out. What's the value coming in? This is our data that's being written to this register. So here's our input to our register. So when this guy fires on register 0, let's say, so we have a 0, 0, which will be D0. That's going to tell register 0 here to load. What will happen? Whatever the value that was coming into our write data, this 8 bits, that guy will flow into this register. Now notice here that this data, so let's just call this 8 ones, just for the sake of argument here. So we have 8 ones coming into our register file here. Those 8 ones are all knocking at the door of every single one of these registers. So just follow this green line here. So this is an electrical signal. This guy's not like stopping it. So we have 8 ones waiting at the door here. We have 8 ones waiting at the door here. We have 8 ones waiting at the door here. We have 8 ones waiting at the door here. And they're going to continue to wait until their particular register, if you think of these as houses, till somebody hits the load button on that house. So as soon as load hits here, when this decoder says load, this door opens, letting those 8 ones flow in. That's the value of this 8-bit register. None of these other ones opened yet, because these guys only open when this guy opens when the input to this decoder is 0, 0. This guy opens when the input to this decoder is 0, 1. This guy opens when it's 1, 0. This guy opens when it's 1, 1. Okay, that makes some sense? So we understand how the load works. We understand that data is coming into our register file here. So this is a register file, and if you think back to our MIPS processor, what's a register file? We had 2 things. We had register file and we had data memory.
So collections of registers.
Collection of registers. So if we're looking at this as a super ghetto MIPS processor, what am I looking at? I'm looking at a MIPS processor that only has 4 registers. It's pretty limiting, right? With only 4 registers. Even the one we wrote had, I don't know, what did it have? 12 registers, 20 registers, whatever. We had a bunch. More than 4, right? We had more than 4 registers. So this is a super, super, super simple MIPS processor. But understand that we can't understand this diagram, this super simple diagram, unless we understand the individual components of this diagram. So do we at least understand the individual components better now than we did an hour ago?
Yeah.
Let's go with that. All right. So if we think about the purpose of a register file, so you go back to our MIPS assembly code. The register file is a collection of registers. What do we use registers for? We use them for storing data that we're going to be doing mathematical operations on soon, right? So usually when we load a value, we're loading a value into only one register at a time, correct? Mm-hmm. So the idea here would be we're loading a value into a register file. Think of it as this bucket with a collection of registers in it. So I'm loading a value into this register file, but I want that value to really just flow to one of the registers that's inside of there. So based on what your input is from your instruction, this is the instruction that's flowing into the processor. These decoders will fire in such a way that only the register that we had targeted opens his door. So the data that we were feeding in here, which is banging on the door of every one of all 4 of our registers. If we had 8 ones here, it's waiting at every one of the registers, just waiting to load into it. But we only open the door on one of the 4 based on the output of this register. These guys are being unused because this is a simplified, since we only have 4 registers, I only need 4 states.
Yeah.
So this hardware here actually supports 12 states. So I have enough guts here to support 12 registers.
Those are not.
4, 8,
This is
12.
This for the read.
But I have enough guts. If I'm doing loads, I have enough guts to support 12 registers. Make sense? Okay, so I have enough guts to support 12 registers with these decoders. We're only supporting 4 of these registers because we have to support both reads and writes. So for loading data, I can load into one of 4 registers, and that is supported with a single 2x4 decoder that only opens the door of one of my 4 registers. That makes sense? Now, these decoders here are going to be probably operating off very similar inputs to the guy up here. That is to say, which register are we reading from? So he's going to toggle which register are we actually reading from. So notice this guy here, like, again, it's a 2-bit encode, so 4 unique values. They flow out D0, D1, D2, D3 on RA. So this is RAD0, RAD1, RAD2, RAD3. So this guy handles our reads. Now we have RB. So this is another value. So we have 2 different, remember I said earlier when we looked at the high level here, and we're going to take a break in a second. I know we're in an hour. Let me just finish this thought. So we looked at this earlier. I said, hey, from our register file, it's possible that 2 different things might be interested in outputs, right? I can write something and read 2 things all at the same time with this supported hardware. I can do a single load and 2 reads with this hardware. All right. So what are we actually doing as our output? Notice this guy here and this guy here. And what's this? What does this guy look like? What primitive does this look like? That's our tri-state buffer.
Yeah.
Remember, that's our 1-bit, the Netflix buffer. Netflix. All right, so only when RAD0, only when this guy fires, does a 1 get delivered here, where the output of this register is allowed to flow out. But the output of this register is only allowed to flow out if his load is firing. Right? That goes back to our previous thing where we have the expected result of Z. So just because I've opened this gate and said this value can flow out, doesn't mean that I actually have a value from here yet. Make sense?
It always has a value.
Because this guy has a static state.
Yeah.
This value doesn't get changed until a load happens. But as soon as I load a 3 into this register, that 3 is available as long as there's electricity flowing to this register. So as soon as I open this gate here, I am not removing a value from here. That only happens. The state of that register only changes on a load. But I can read the current value of a register. If I say, give me the value of register 0, that doesn't remove the value from register 0. I just get a copy of its current value that I can work with. Does that make sense? So our reads allow us to trigger something, 2 different inputs, that will give us 2 different outputs. But notice that both of these outputs are hooked onto the same pipe. So if you think of this like a soda machine, right? We sell lemonade? Yeah, soda, whatever. So we got soda flowing out of here, but it's blocked here and it's blocked here. Right? So if this guy's a value 3, let's say 3 is Mountain Dew, Diet Mountain Dew. So if this guy here, register 0, holds a 3, Diet Mountain Dew is flowing to right here, and Diet Mountain Dew is also flowing to right here.
Yeah.
But not until we fire a bit here do we release that buffer. It's equivalent to pushing the little button on the Diet Mountain Dew thing to get the stuff to come out, right? And that's when our value is actually read from a register. So when we give our inputs here, we say, what register do I want? What register do I want? And that controls what comes out here and what comes out here. So I can read from 2 separate registers, or actually I can read from the same register twice if I wanted to. But I could read from 2 separate registers at one time with this register file, and I can write to 1 register at a time. Make sense?
So then this is just like a very small subset of essentially what we did and how computers work.
Correct. This is a MIPS processor that only has 4 registers, and all it knows how to do is load values and read values. So why the heck is it so complicated looking?
I know, did they like actually build out these graphs like when they were thinking about computing?
Yep.
That's just insane to me.
This is how it's built.
But now that you look at it, I realize you have to follow all these wires and stuff, but now that we understand what these individual primitives are, it is easier to read, isn't it? It's still confusing, right? You got lines all over the place and things like that. So you got to take your time and kind of see, okay, what connects to what. But you have no chance of understanding this unless you know what this guy is, and you know what this guy is, and you know what this guy is. So now we're seeing 3 different primitives that were introduced to us earlier in the chapter working together to solve this larger problem. All right. I think that gets us to the end of this chapter-ish. I think if we understand this whole chart, we understand the rest of this chapter.
Yeah, no, the rest.
This chapter.
This one is.
Yeah, 5.5.
Yeah,
We understand how register files work now.
Yeah, but not.
Okay, got it. Yeah, I got it. Okay, so let's take 30 seconds. Let's take 5 minutes, 6 minutes, 5 minutes, 4 minutes.
More complicated.